Good morning and welcome to another exciting episode of Dave Does Math from Home. Today we're doing Calc 1, Chapter 1, Function Review. This is the one section that we're not going to split into different sections. Like the actual Chapter 1 in the Calc textbook has like 5 or 6 different sections in it for various different things. We're going to mash them all into one, and we're going to do this all in one thing, because all of these topics should be review from pre-calculus. This is all stuff we've done before. We're just going to review it. So we're going to go through it pretty fast. Just to open us off with a word of advice. This homework assignment has 30 problems. Many of them are challenging. Do not sleep on this homework assignment. Do not wait on it and hope that it will be easy to knock it out at the last minute. That is absolutely a mistake. Start working on this as soon as possible. When you get to questions that are challenging or that you don't remember how to do or you're confused about, bring them to me right away. We'll get that sorted. Just be very proactive about this, because if you wait till the last minute, you're going to have a really bad time, and then you're going to start off the entire semester behind. And this is a summer class. We only have 7 weeks. Don't do that to yourself. Get this done right away. So, there's a bunch of stuff we need to talk about in Chapter 1. The first thing I want to talk about is shapes of functions. So, one of the big main goals of pre-calculus was to sort of leave you with like a library of function knowledge that you could draw on. So that if you start to do calculus on an exponential function, like as soon as you recognize it as an exponential function, you know things about it. You know how it behaves. You know that it's going to have a horizontal asymptote somewhere, probably to the left. If it's an inverted thing, then it would have the horizontal exponent to the right. And then on the other side, it's going to swoop up if it's positive, down if it's negative. These are just things that you should know and recognize about all exponential functions when you see an exponential function. Same with like a logarithmic function. You should know approximately, if you see a logarithmic function, you should know how that behaves. That's just sort of like the baseline expectation I have of you going into calculus. So we're going to start off with doing a review of a bit of that. And we'll start with polynomials. Generally, polynomials means no weird stuff. In terms of functions, this means no negative exponents or division by variables, no radicals or fractional exponents, no trig, no exponentials, that means variable exponents, no logarithms, no weird shenanigans. It's just very simple, straightforward numbers, exponents, positive whole number, numbers, variables, positive whole number exponents. That's what polynomial means. And we have this as a category that basically means no weird stuff because polynomials are really, really easy to do calculus with. Polynomials are always very well behaved. They're always smooth. They're always continuous. They're always differentiable. These words will mean something to you in a couple weeks. Right now they probably don't. But that's why polynomial is a category and why we say that they have no weird stuff. This is not an official definition. This is an idiosyncratic description of mine. If you try to take this to other math teachers and say polynomials mean no weird stuff, you might get some funny looks. But I think it's a good description. Polynomials typically do some wiggles. So if we have something like y equals x, let's say x to the fourth minus 16x squared, you're going to get a couple wiggles out of this. End behavior is up in both directions. Probably going to have a double root at 0 and 2 other roots at 4 and negative 4. So we're probably doing one of these numbers. Has some wiggles to it. But it has a finite number of wiggles and has some end behavior eventually. This is polynomials. I can hear some of you thinking, a finite number of wiggles. That sounds boring. What if I want an infinite number of wiggles? Good news, my friend. I got an infinite number of wiggles right here. Trigonometric functions. This is your sines and your cosines, technically your tangents as well, but tangents are really weird. They do weird things. They behave in weird ways. I'm not going to deal with tangents much. We're going to deal with sine and cosine a lot. So you might see something like y equals the sine of x. That starts in the middle, goes up and down. This function is periodic. And periodic means an infinite number of wiggles. Wiggles forever. Y equals cosine x. Does basically the same thing, but it starts at the top and goes down instead of starting in the middle and going up. Both of these things, unaltered, have peaks at 1 and minimums at -1, and a period from 0 to 2 pi. Oh, that's not where the period ends. There it is. There's a full period. From 0 to 2 pi. This would be 1 and -1. These are the basic graphs. You know we're probably not going to deal much with the basic graphs. We spent a long time in pre-calculus learning how to mess with these guys, how to stretch them and shrink them and do all kinds of stuff. We're going to get to that in just a second. First, I want to talk more about function types and get a new marker. Alright, next up we have exponential functions. Those guys look like y equals 2 to the x, or y equals e to the x. Exponential functions typically have horizontal asymptote in the back end. Unaltered exponential functions always have an asymptote of y equals 0 and an intercept of 1, 0, 1. E to the x looks exactly the same. It's a little steeper. Still 0, 1. Still y equals 0 as an asymptote. You can sort of flip this around backwards if you do a fractional base. So y equals 1/2 to the x. Has the same shape but goes backwards because that's the same as 2 to the negative x. And putting a negative sign up here flips things back and forth. Logarithmic functions look like y equals the natural log of x, or y equals the log base 3 of x, something like this. They look like exponential functions that have been flipped sideways. So they have vertical asymptotes at x equals 0 and intercepts at 1, 0. And instead of being flat back here and swooping up, they are vertical-ish over here and swoop sideways. This, once again, has the exact same shape, just a little steeper, or a little less steep, maybe. This one should be steeper. Natural log should be a little bit steeper than log base 3. So this is, again, 1, 0. And this is again x equals 0. We should also mention rational functions. They look like a polynomial divided by another polynomial. Like y equals x plus 1 over x squared minus 2x minus 3. Something like this would be a rational function. We're done graphing these. You don't have to worry about me asking you for graphs of this. We'll finish that in pre-calculus. But we should know what they are and how they behave. Things that make the denominator equal to 0 will result in vertical asymptotes on a graph. Things that make the numerator equal 0 will result in x-intercepts. The ratio of the leading terms will give you its horizontal asymptote if it has one, its end behavior, and the constant terms will give you its y-intercept if you wanted to graph. Mostly you should just know that these things have vertical asymptotes in strange variable places. Sometimes it's possible to make rational functions that don't have vertical asymptotes. They're kind of like a wild card. They get messy. They're not very consistent. They do strange things in strange times. That's why we're not going to really do a lot of calculus on them. We're going to do calculus on things that are, again, well-behaved, smooth, continuous, differentiable. That is not this, a lot of the times. But they're still part of this function library. They're still pretty important. You should know what they look like. What's left? What was the big flavors of function we needed to deal with? We could talk about power functions briefly. If I had a function marker, we could. Power function looks like y equals x to some power. We'll go with n for now. The difference between this and a polynomial is that n does not have to be a whole number. So like, if n is a whole number, like 2 or 3, then this is both a power function and a polynomial. But for power functions, it could be something like x to the 1/2. And that is the square root of x. Looks like this. Or we might get something like y equals x to the 1/3, which is the cube root of x. And that looks sort of the same. It's a little deeper, it's a little more boxy, and it has a back end. So if you're taking cube roots, you can do that to negative numbers and you'll get negative numbers. If you're taking square roots, those end at 0. So power functions are going to be a thing that we will play with from time to time in calculus. Not something we talked about in pre-calculus at all, because they're simple. There's not much more to it than this. But you'll be seeing these. That's it for our function library. I still need to talk about ways that we're going to mess with these functions, so stay tuned for that. And then we need to talk about difference quotients. So stay tuned.